Welcome to the Explainer. So let's jump right in, shall we? Imagine, just for a second, a bustling orchestra. Now, without a conductor, the musicians would just be playing random notes at random times, right? Total chaos. Well, your cells are actually a lot like that orchestra, and today, we're going to master the microscopic conductors that orchestrate the entire symphony of life processes inside you. Enzymes. Understanding the precise mechanics of enzymes is absolutely crucial for your O-level biology exams, especially when you're dealing with metabolism and homeostasis. Nailing this concept could easily be the difference between a B and an A grade.
Okay, here's a question that might just shatter a pretty common misconception right out of the gate. Did you know that enzymes can not only speed up chemical reactions, but actually reverse them? Yeah, most people think of enzymes purely as biological accelerators, just pushing the gas pedal to the floor. But as we'll see today, they also have this unique ability to push things in the exact opposite direction, acting as master balancers to maintain your body's delicate internal equilibrium.
To secure that A grade, we've got a clear roadmap. 1. We'll meet your biological conductors. 2. We'll look at the activation energy ramp. 3. The lock-and-key mechanism. 4. Denaturation through temperature and pH. 5. The reversible seesaw. And finally, 6. Acing your biology exam. Let's do this.
Section 1. Meet your biological conductors.
By definition, enzymes are what we call biological catalysts. If you take a look at this simulated protein structure we're bringing up, you'll see almost all enzymes are proteins. Their primary job? Speeding up chemical reactions, which is absolutely vital for keeping processes like digestion and respiration moving fast enough to keep you alive. And the really crucial point is stamped right there at the bottom. They do this without being consumed in the process. They are the ultimate reusable tool. Section 2. The activation energy ramp. Now, this brilliantly illustrates the physics of how they actually work. Think about activation energy. In step 1 here, without an enzyme, notice that massive hill? That's a high activation energy barrier. It's literally like trying to push a heavy cart over a steep wall. It takes a ton of initial energy just to get the reaction started. But watch what happens as we progress to step 2. Notice how the enzyme steps in and physically pushes that barrier down? It introduces this lowered energy ramp. By flattening the curve, the enzyme drastically drops the required activation energy, making it incredibly easy for the reaction to simply roll forward.
Section 3. The lock and key.
So how do they know which of the millions of cellular reactions to trigger? It all comes down to intense specificity, which is beautifully reflected in their scientific naming convention. Notice that ACE suffix we've highlighted? Whenever you see a word ending in ASE in biology, you are almost definitely looking at an enzyme. And the first part of the word? That tells you its exact target. For example, lipids, or fats, are broken down by lipase. Proteins are broken down by protease. They don't cross over. A protease will completely ignore a lipid. Why are they so specific, though? Well, it's all about physical geometry. Let's track this step by step. In step 1, the target molecule, called the substrate, approaches. Think of this as the key. Moving to step 2, watch this perfect geometric docking process. The substrate fits flawlessly into the enzyme's active site, which acts as the lock. If the shape isn't a perfect match, literally nothing happens. Finally, in step 3, the reaction is catalyzed, the new products release, and the enzyme is left completely unchanged, just waiting for a new key. Section 4. Denaturation, temperature, and pH. Enzymes are incredibly sensitive to their environment, especially when it comes to temperature. For human enzymes, there is a magic number, 37 degrees Celsius. As we can see here, this is our optimum temperature. It is the exact thermal condition where human enzymes function at their absolute, most efficient peak performance. But look what happens when we contrast that peak function against extreme heat. On the left, everything is running smoothly at 37 degrees. But zooming in on the right during extreme heat, notice how that violent thermal energy is physically breaking the delicate structural bonds of the protein. The active site is warping out of shape. The lock is literally melting. When this happens, the substrate key can no longer fit. This permanent destruction of the enzyme's shape is called denaturation. Once an enzyme is denatured, it is broken forever. And temperature isn't the only threat here. You see a very similar structural warping with extreme pH levels. Comparing optimum pH with extreme acidity or alkalinity. A highly acidic or basic environment will also denature the protein. It fundamentally destroys that specific lock and key geometry.
If the pH drops too low or spikes too high, the active site warps, and the whole biological assembly line just grinds to a halt.
Section 5. The reversible seesaw.
Now, back to that hidden talent we mentioned at the start. Enzymes don't just act as one-way streets. They act a lot like a seesaw, catalyzing reversible reactions to maintain a dynamic equilibrium inside the cell. Notice how these pathways are pushed to the right to form products, but can then shift and push back to the left, breaking those products back down into reactants. Depending on what the cell needs in that exact microsecond, the enzyme acts as the fulcrum of this seesaw, constantly balancing the chemical equations backward and forward to maintain strict cellular homeostasis.
Section 6. Acing your biology exam.
Let's debunk the two most common exam mistakes right now so you don't lose any marks. First, never write that enzymes are used up or consumed in a reaction. Look at that bright callout. They are reusable. They catalyze the reaction and pop out the other side perfectly intact. Second, do not fall into the trap of thinking all enzymes share the exact same optimum temperature and pH. Yes, human enzymes love 37 degrees Celsius, but an enzyme from a bacteria living in a boiling hot spring, its optimum temperature might be 80 degrees. Every type of enzyme has its own highly specific environmental needs.
All right, let's do a rapid, checklist-style recap of our entire session today for ultimate retention. 1. Enzymes are biological catalysts, mostly proteins. 2. They speed up reactions by lowering that activation energy ramp. 3. They follow a highly specific lock-and-key fit, identifiable by the ACE suffix. 4. They denature or permanently lose their shape at extreme temperatures or pH levels. And 5. They act as reversible balancers for cellular equilibrium. Lock this checklist in before test day. And that brings us to the end of our breakdown, but I want to leave you with a real-world scenario to think about. If human enzymes denature and break down when pushed past their 37 degrees Celsius optimum, what exactly happens to your cellular reactions and your metabolism during a severe, prolonged fever? How much heat can your microscopic conductors take before the symphony stops entirely? Keep exploring the microscopic world, and we'll see you on the next explainer.